Friends, fellow Earthlings, and those awaiting some of the knowledge that's bound up in materials and other worlds, just waiting to be returned back here to Earth, much like the words in ancient books being brought home from the library. Welcome to Ask An Astrobiologist, the show that celebrates the science and the scientists involved in our quest to understand the nature of life. I'm your host, Dr. Graham Lau, and we are, of course, brought to you by the NASA Astrobiology Program and SaganNet.org. As always, we want to say a huge thank you to all of you out there who watch our show, who reach out to our guests, to myself, to interact and ask all of your questions about the NASA Astrobiology Program, about astrobiology as a field of understanding, about this quest that we have to understand what life is, where it comes from, and where we're going. We want to say a huge thank you this month to Dr. Charles Liu of @Luniverse, for reaching out and sharing about our show in several places online. We always appreciate that kind of support. So if you want your own shout out on our show next month, please share about our guests, about the upcoming episode, share your questions online. We love to interact as much as we can to make sure that we're getting your questions to the astrobiologist that we bring on the show. Now, today's episode is going to be a bit of a romp through astrobiology in a bunch of directions, focusing in on one very specific realm of sample return. We have joining us today Dr. Lindsay Hays. Dr. Hays is a program scientist for the NASA Astrobiology Program, the deputy lead scientist for the Mars Sample Return Campaign, and a program scientist for the DAVINCI mission to explore Venus. Lindsay's scientific background includes work on lipid biosignatures for things like mass extinctions, evolutionary radiations, and studying photosynthetic organisms in hot springs. She spent time at JPL in the Mars Program office, where she was a sample return science systems engineer and also worked on science activities for the Humans to Mars program. So thank you so much for joining me, Lindsay, and welcome to Ask an Astrobiologist.
Morning, Graham. I'm glad to be here.
It's so awesome to finally have you on this show, being so involved in the NASA Astrobiology Program, but having so much expertise and experience throughout the realm of astrobiology, from your own research to now helping others in their research and being involved in so many missions and mission development. Before we talk about things like sample return and your research and your own career, I'd love to know what inspired you to become involved in this career in the first place. What was the thing that got young Lindsay interested in becoming an astrobiologist?
I think the first thing to say is I'm from Jupiter, and that actually means I'm from Jupiter, Florida. It's a little town sort of at the northern part of Palm Beach County. But one of the really cool things that happened when I was growing up is from Jupiter, you can see launches from the Space Center, from the Kennedy Space Center. And so growing up, whenever there was a shuttle launch or anything like that, you could go outside and you could see the trails from the rockets and the lights from the rockets and that sort of thing. And so from a really young age, it just was natural to me to think there are people going to space, right? There are people going to space all the time. This is just part of our exploration. And science and biology and all of those kinds of things, I always found very, very interesting. And so, some combination of knowing that we were exploring space, just knowing that it was sort of part of what we were doing as a nation was really exciting. And then, getting involved with science fiction and reading a lot as a kid, it was kind of a bookworm. And then, I had a fantastic biology teacher in high school. Dr. Lisa Rayford was the biology teacher. She is now one of the associate principals at the school that I was at. And just, knowing that these are some fantastic things, I was so fascinated by the concept of life elsewhere and how life evolved on our planet and what are the ways that we can understand those two things as they're linked.
Oh, that's awesome. Seeing these lights in the sky, reading great books to inspire you, but also having great people in our lives is so inspirational when they really do help us kind of, find those pursuits for ourselves. So that's very awesome. You did your undergraduate and your graduate work both at MIT and a postdoc at Harvard. You interned at JPL. I'm curious what the trajectory was that kind of got you interested in going from, academia into government and really being involved and now working at NASA headquarters.
When I was an undergraduate and a graduate student and a postdoc, I was really lucky to be able to work with some fantastic researchers and people who are and were really pushing the envelope about what we understand about life and how it evolved and such. And while I was there, I recognized that as much as I loved, sort of being down and in and doing the science itself and, being at the bench and being the first one to see some result and know that, I was the first person to sort of put all of these pieces together and understand this particular aspect of science. I also knew that for me, some of the higher level, long-term programmatic, how are we going to do this? What is this thing? Think strategically 10 years down the road. Where do we want to be going with this? Some of that kind of work I found really exciting. I really enjoyed not just thinking about what's happening right now, but sort of thinking towards the future, making sure that we sort of understand how we got here and all of that sort of thing. And so it was actually my postdoc advisor at Harvard, Dr. Pearson, who suggested that if it was not my absolute passion to continue doing lab research, that I explore some other options, that I think about, what it would be like to work in industry or think about what it would be like to work in government. And she really encouraged me to go out and talk with different folks and think about, some other options. And I had an opportunity to talk with Mary Wojtek, Dr. Mary Wojtek, who was of course, the senior scientist for astrobiology. And she said, we have this great opportunity to serve as a NASA postdoctoral management program fellow at headquarters. Why don't you come and see what it's like? Put in an application. If you're accepted, you can come work at headquarters with me and Dr. Michael New, who is the exobiology program lead and an astrobiology discipline scientist at the time. And it turned into this fantastic opportunity to spend a year at NASA headquarters in Washington, D.C. And I absolutely just fell in love with the kind of work that we were able to do. And the sort of big picture, thinking about all of the different pieces that come together in astrobiology and all of the different things that are involved in that, all the different researchers and topics and all of that. I was able to work on the 2015 NASA Astrobiology strategy, the science strategy. And that was just a fantastic opportunity to really get in and work with all of these scientists and think about the future. So, a combination of not really being sure where to go, some good advice, and taking advantage of opportunities that I was able to take advantage of.
I love that so much. Carl Sagan once shared this old war song that says, "I don't know where I'm going, but I'm on my way." And it's always kind of nice to have that trajectory of having an idea of where things could be, but also kind of having no idea in the end. And I do love hearing that there are other options. I think sometimes for young people who are interested in careers in science and engineering, they sometimes feel like, the only trajectory is undergrad, grad school, postdoc, professor. There really are a lot of directions you can take along the way and stem out into different fields. And so it's always great to hear that there are other options, and there are options that include working for the government and working for NASA.
Yep. And I'll say as a graduate student, that was the kind of thing that I was really struggling to find and sort of looking for those types of activities. So yes, 100%. It's a good reminder that there's a lot involved in science that's not bench work or field work or, modeling work and stuff like that. That's bigger and broader.
Absolutely. Now, I do want to speak about your involvement in things like sample return missions. However, before we get there, I do want to speak a bit about your research and connecting your research to some recent activities. Myself being from the geomicrobiology / geochemistry realm for my own PhD research, I had this experience when I first went to my field site. I had spent many years reading papers about this place in the high Arctic. And then when I finally got there, it was this very human thing happened. It was a much different experience seeing the site with my own eyes and my own senses, tasting and smelling and experiencing this realm. It really made me understand the research in a much different way than I could with just pictures from satellites or from helicopters and aircraft and things like that. And for you yourself, you recently went along with the Mars Exploration Program to Western Australia to study things like stromatolites in Western Australia and these very old formations. And that is tied to your own background in research. I'm wondering if you can share your own human connection from your research to actually traveling to those sites with us.
Yeah. So, my PhD work was trying to understand sort of the causes and the environmental effects that were related to mass extinction events. But sort of while I was in that time as a graduate student, the stromatolite, let's say the debate about microfossils and trying to understand exactly what we're seeing and how we understand what these ancient stromatolites and these other microfossils that are from Western Australia, what they can be telling us, sort of what they mean, what their significance is as part of our sort of understanding of the history. This trying to look back in time and understand what was happening in these different microbial communities and what types of things that were recorded from the ancient past that then are continued into the future that we can find evidence of today. That's really related to a lot of the work that I was doing. And this whole debate about these things was a real, sort of active in the literature around the time that I was a graduate student. And so being able to, walk out to see some of these stromatolites that are billions of years old, to understand, to have that sort of understanding of conceptually of how they formed and what they meant and why they were important. That was something that I could get from the papers and in the literature and talking with people who'd been there. But actually being able to walk out in the field, it was very rainy on the first day that we went out. So despite the fact that it was a bit cool and quite rainy and not very pleasant to be outside, there was just this overwhelming sense of excitement that I had at being able to see and touch and observe and really get a sense of, this is what it is. This is actually the record. This is how we understand what the history of life on our planet is and how it has changed over time. And so that was just a really fantastic experience.
I love it so much. Yeah, I'm super jealous. I've not been to Western Australia to see some of these sites yet. I do know with our NASA Astrobiology YouTube channel, there's a recent video created by Mike Toyon, including the team who went on the trip, called The Australian Outback and NASA's Search for Life on Mars. Definitely worth a watch for our audience to see even more of the action going on in Western Australia. We did ask all of our audience through a poll on YouTube before the show. We gave them a few of the formations that can be seen in these Western Australian sites and asked what the oldest were. They had Trendle locality, the Dresser Formation, and the Minthina member as possible options. Indeed, it was the Dresser Formation for our audience that was the oldest, even though that one didn't win the most votes. It was 3.48 billion years old at best estimates right now. So not as old as the Earth. Remember that the Earth itself is 4.56 billion years old, but due to the Earth's own dynamic activities, we don't have rocks that are as old as the planet on the surface of the planet outside of meteorites. But there are ways of sampling things that are even older by doing things like sample return from other worlds. And so, Lindsay, I think I really want to stress now a bit of, one, we can connect maybe Australia to things like sample return from Mars and how those things are relevant, like looking into the environment on our own planet. How does that help us to really understand samples from other worlds like Mars?
That's a great question. And that also was one of the main reasons that we went to Western Australia. Honestly, what it is when we're thinking about the search for life, we're thinking about astrobiology, we're thinking about trying to understand what our planet's history was like and what we might be looking for when we're looking for life elsewhere. Context is key, right? It is absolutely important that if you find something that you think may be indicative of life, that may be a biosignature of some sort or another, that you understand where that sample came from. And what were the sort of looking at the geological context, understanding from the other rocks around it, where, how that sample came to be there, what the depositional environment was the temperature or the other environmental conditions consistent with what we understand life to be able to live in? Was there anything that happened to the rocks after these samples were deposited? Did they, were they subject to sort of mountain forming events where there's these deep temperatures and pressures and things like that may have altered the features that we're looking at? Just sort of what not only was the environment when those rocks were deposited, but then since then, what has happened to those rocks? And if you don't understand that context, you don't really understand what you're looking at, basically. And so when we think about sample return as a way to understand, or as a way to sort of to get at our search for life and NASA's search for life, you really have to be able to collect samples for which you understand that whole history. And so, the exciting thing about going to Australia was walking around and seeing these, fantastic red rocks and these great green plants and these red soils and everything like that. And realizing that, this is a fantastic feature to look for stromatolites in that example. But if we were on this, if we were in that place, imagine the plants are gone. Imagine it's just the rocks. You're driving around with a rover. How would you look for a section that would be useful for you to understand whether or not there were biosignatures in the area, not just on this rock, but in this whole area? And so, being there and sort of, standing up on this hill, having these fantastic stromatolites at your feet, looking around and recognizing that this is one of the few places in this area that these are preserved this well. Okay, what's different about this hill? How would we have picked this hill out if we were, driving around with Perseverance or something like that? And so that opportunity to be there in the field was a sort of additionally fantastic aspect about that work, and be able to really think about what the value is of that context.
I love that. Yeah, context is key, as you said, for making those connections. Yeah. And I personally have seen this question a lot, especially of late, about sample return is, why not just send better robots? Why don't we just send robots that can do the things that we return samples for? I wonder if you can speak to that. Why is sample return so important for us?
Yeah. So I think of this as sort of, there's two answers that I often think about. And the first one is a very simplified version. And that is when you bring a robot to space, and you go to the surface of another planet or somewhere else, you have a lot of limitations on what you can do. You have a lot of limitations on the power, on how big the thing can be, right? Because you need to launch it from the surface of this planet, and there's limitations about the size of the rocket and stuff like that. And so, I think about it like when you travel somewhere, right? You bring the travel-sized version of whatever you have. It's not the full complex version. I used to liken it to like a hairdryer, right? You don't bring your full, fancy hairdryer. You bring the small little travel-sized one. And so you have all these limitations of what you can bring when you go to another planet because of all of those things. Now, when you go to another planet, of course, you have all of the rocks to choose from, right? Any rock that you can get to, you can investigate with whatever spacecraft you have. But when you bring samples back, you have a limited subset of samples that you're bringing back. So you need to select them very carefully. But when you have them back here on Earth, you can create a very careful and sort of iteratively designed process for investigating those samples. And throughout that iteratively designed process, right? Okay, we learned this thing. Now what do we want to do next? Okay, we learned this thing about it. Now what do we want to do next? You can bring to bear all of the scientific equipment that we have right now on this planet, and all of the scientific equipment that we may develop in the future. So, your samples, when you send a spacecraft, you have sort of an unlimited almost sampling capability. But what you can do with those samples is very limited by what you've brought with you. The inverse is true when you bring them back, right? You have the limited subset of samples, so you do need to select them very carefully. But once you've got them back, you can bring to bear anything that you can imagine and design and create any of that scientific investigation to those samples. And so it really not only expands, the value of those samples in the short term, but in the long term, and it really makes it a much more valuable prospect to be able to bring all of that scientific knowledge to bear.
I love that so much. And I love your analogy too of traveling with our smaller kit. My beard care routine when I travel is a much different routine than here at home, because of that nature of having more options for the kinds of instruments I will take into that game. So I love that so much. And obviously right now, a lot of people are thinking about how we're going to be using high resolution instruments of various kinds on some samples that just came back to Earth. We just changed the number of worlds we've sampled from and have returned successfully samples to Earth. And you were in Utah this weekend for the OSIRIS-REx capsule returning and landing and bringing those samples back. As a connection to Mars sample return, I wonder, can you make that connection for us and let us know what was it like to be out there and waiting for that capsule to come down safely?
Well, I'll answer the second question first. It was absolutely inspiring and exciting and just really fantastic. I mean, I've been lucky enough to attend a number of, launches of different missions and such. And to me, that's always this awe-inspiring opportunity. I mean, the amount of understanding that it has taken to get us there, the amount of individuals, the number of individuals who have contributed to every step along this process is just, it's a remarkable show of teamwork, sort of the desire to explore and to know more and all of that. I always get a little teary-eyed at launches, and I did at the sample return as well, because, this is just, this is the exact exciting, exploration thing that humankind has been continuing to do throughout the ages. So it was just a fantastic opportunity. The connection to Mars sample return is, hopefully we'll be doing this same kind of thing again with a few changes in hopefully just about over a decade is when we'll be bringing those samples back from Mars. So it was a great opportunity to sort of be out there, see how operations work, really, visualize, this is what happens here, and then this kind of thing happens, and this is how this is how somebody goes to the place where the capsule has come down, and these are the kind of checks they do, and sort of every stage along that way, and all of the different steps that happen when we bring those samples back. There's going to be additional things that'll happen with Mars sample return because of the nature of Mars versus Bennu as a place that we're bringing samples back from. But just, being there was this opportunity to sort of really, it kind of became real. Okay, Mars sample return is the next thing we're going to be working on. So it was a great opportunity, and it was a really, just exciting to be there.
Oh, I love it so much. I know a bunch of us who couldn't be there in person were watching online and sharing all over the interwebs and posting things actively in social media. And so it was so good to see, as always, so many people sharing about these endeavors in space exploration and the activities that NASA and other organizations are up to. We did ask our audience another poll on YouTube, basically asking how many worlds, how many celestial bodies have we sampled from and brought samples back to Earth? Interestingly, most of our audience thought it was only 3. Indeed, the answer is 6. And there's even a little bit of hand waviness there for everyone watching. 1, we have sampled from the sun. And so we count that as a celestial body. It's a star. And so we have sampled material from the solar wind itself. We've also sampled cosmic dust, much of which should be coming from the sun, but also potentially outside of our own solar system. But then, of course, we have many lunar samples brought back from Apollo, the Soviet Union, and more recently Chang'e 3. We also have things like Wild 2. A comet was sampled with the Stardust mission. Hayabusa and Hayabusa 2 were missions that sampled from 2 other asteroids as well. And so Bennu is the 3rd asteroid we've sampled from. And so in total, we have 6 celestial bodies that we've sampled from. And now with this concept of Mars sample return, it might soon be 7. And so I do want to speak a little bit about why we might treat those samples a little differently in coming back to Earth. Specifically, and I'm sure you knew this might come up, but there are some fears maybe from some people about bringing samples back from Mars. I wonder if you can speak maybe to those fears and possible issues with returning samples from a world like Mars.
Yeah. So, of course, Mars is the first place that we have sampled that we think had the potential to be habitable at some point in its history, right? We don't really think of, we are interested in those other solar bodies as sort of a context setting. Again, there's that word, as a way to understand, all of the different processes within our solar system. But Mars is the first place that we will sample from where we think the whole point of Mars sample return, or one of the major goals of Mars sample return, I'll say, because there's other points too, but one of the major goals is to understand whether or not we can identify biosignatures from past life that may have existed on Mars. Just to be clear, we are not looking for extant life. Mars 2020, Mars sample return, we're not going there to try and find things that are alive today. We're going there to look for the kind of biosignatures, perhaps, hopefully, maybe, that we were looking at when we were in Australia, right? The kind of biosignatures that say there was life here in the past. Some record of that life has been preserved, and we can find those rocks and understand what we're looking at. So that's one of the goals of Mars sample return. But because we believe that there was the potential that Mars was inhabited, or habitable at least, I'll say they believe there is a potential that Mars was habitable in the past. We hope that it was inhabited. That we share concerns, and therefore we are doing everything that we can work on. We are working very hard to make sure that we meet what we call the planetary protection guidelines. Now, planetary protection is an internationally agreed upon set of rules and regulations. Any spacefaring nation who is bringing samples back or going to a place in the solar system has to pay attention to these rules. They're called COSPAR. These regulations help us understand, what types of things we need to be careful about. How much Earth microbes we can bring elsewhere. If we're bringing samples back, what kind of things we need to be careful about, and all that kind of stuff. So, as part of Mars sample return, we are working on planetary protection and what we call backwards planetary protection. That means bringing stuff back to Earth. And we're working on backwards planetary protection, and we're thinking about, sort of multiple layers of containment, multiple layers of, keeping these samples isolated and in multiple layers of isolation as they make their way back. Once we get them here on the planet, sort of bringing them to a facility that's specially designed so that not only do no material from within those samples leave the facility, before we're able to do an assessment, but also, we have to protect those samples. It's sort of a two-way contamination concern, right? We don't want anything from those samples to get out, but because we're looking for life on these samples, we also don't want anything from Earth to get onto those samples, right? The whole point is to look for biosignatures, and if we find biosignatures of ourselves, that kind of complicates the process. So, we're creating this facility that has these two-way, contamination concerns, and make sure, and then we're also designing what we call a sample safety assessment protocol. What this framework that we would think about, what are we looking for to see whether or not we see evidence of life past or present on these samples? What measurements would we make? How would we look at the result of those measurements? How would we interpret those measurements to deem that these samples are safe, that they don't have any evidence of any Martian life on them right now? And in the event that we, that's a little bit uncertain, or that we have any concerns, we can always sterilize the samples before they're released for, for future work. So we have sort of multiple layers of containment for these samples as they come back. And then once they're back, we would have multiple ways of assessing those samples for the potential of problems or anything like that, for the potential of anything that we may want to be concerned about. And then if we return an uncertain result there, we always have the ability to sterilize the samples. So sort of multiple steps along the way.
I love that so much. It's good to remind people that if it's worth doing right. It's worth doing well, and making sure that we don't do something foolish along the way. And so, we have these protocols for safety, for planetary protection along the way as well. And I also am glad that you mentioned that we're not really thinking about extant life necessarily. We're not really thinking at the surface of Mars, where these samples are being collected currently by Perseverance in Jezero Crater, that we're looking at living things in the near surface. Personally, a lot of us do think it could be possible there might be extant life on Mars, but maybe much deeper. in the surface or kind of hidden away in pockets, but there really is a lot we could learn from these samples through sample return. The big thing, though, is getting them back, obviously, and bringing them back to Earth and going through this whole process then of making sure we safely interrogate the materials and learn more about them. Before we kind of move into our own questions here from the Faster Than Light segment and our audience questions, which I see questions pouring in, so thank you for our live audience watching right now. Please keep asking questions. Before we get there, can you give us kind of the structure of what sample return from Mars will look like? What does it require to get those samples back here to Earth?
Yeah. So, I mean, Mars sample return is a fantastically ambitious campaign. The first stage, of course, is happening right now, right? We have Mars 2020 that is on the surface of Mars in Jezero crater. It is doing an excellent job of collecting samples and also collecting all of this additional information that will hopefully provide all that context that we're looking for those samples. So that is happening right now. In the current architecture that we're investigating, and again, Mars sample return is still early in development. And so we have sort of our current conceptual architecture, but these are things that may change as we understand more about how all of these things work together. There's a lot of new things that we're developing for Mars sample return. But so the current architecture says that the next stage is to send two different missions. So one of those missions is a sample retrieval lander. That mission would land on the surface of Mars. The current idea and the hope is that by the time that lander gets to Mars, Mars 2020 is still in operation and is able to drive right up to the lander. And then the lander has an arm that would pick up samples and load them into what's called the orbiting sample container, or the OS, right? We like our acronyms, right? So the OS is about the size of a volleyball, say. Right now, we're hoping that it'll be able to hold about 30 samples. So this the sample arm picks up those samples, loads them into the OS. The OS is then closed. The OS is part of what's called the Mars Ascent Vehicle. This is essentially a rocket that sits on that lander. That rocket then gets thrown up into the air and launches those samples within the OS up and into orbit around Mars. Once that OS is released in orbit around Mars, the other mission that was the sort of second stage will be there. That's the Earth Return Orbiter. Now, the Earth Return Orbiter, like the sample arm, is being built by our ESA partners. And so the Earth Return Orbiter would then rendezvous with the OS. On the Earth Return Orbiter is the CCRS, the system that essentially will capture and contain that OS. That's being built with NASA. So with each of these two missions, it's sort of the primary builder is one of the agencies, and the other one is sort of contributing. So there's this great synchronicity to that. So the CCRS will capture and contain the OS, and then the whole Earth Return Orbiter comes back to Earth. As it gets close to Earth, it releases the Earth entry system, which is basically a big shell in which the OS is considered to be right in the middle. And that would then come in to just about the same place that we were watching the samples from Bennu on OSIRIS-REx come in just 2 days ago. That would come in to where the current plan is for it to come into UTTR, the Utah Test and Training Range. Then it gets retrieved on the surface and brought to this facility that we were talking about, where those first stages of curation and understanding what we have and really cataloging the whole set would take place. So multiple different stages along the way, multiple different pieces that are being designed that are sort of new and exciting. There's a number of sort of firsts within this thing, right? It's our first time launching autonomously off the surface of another planet. It's the first in-orbit autonomous rendezvous between two different spacecraft. So there's just a whole bunch of really exciting things. And so, it's a complex process, but it's, as far as I can tell, I mean, this is the kind of thing that NASA does, right? This kind of, let's do this whole thing. Let's do this so that we can make sure that those samples that we're selecting, those scientifically selected samples, have this absolutely extremely well outfitted Mars 2020 Perseverance rover that's making all of these fantastic measurements in addition to collecting all these samples. Let's make sure that we prioritize that aspect, understanding that context is really important. Let's prioritize the scientifically selected aspect of samples. And make sure that when we bring them back, sample integrity is paid, that we pay attention to that we're not going to do anything along the way that would damage those samples. So It's complicated, but it's really exciting. And I think it's the right way to do this.
I love it so much. Yeah, complicated but exciting. Things are complex. I'll admit, back when we first sent Curiosity to Mars, I was kind of against the EDL system. I didn't think the sky crane was going to work. It sounded too complex. It sounded impossible. Yeah, exactly. But if we think we can do it, NASA engineers will work their butts off to make it happen, and I love that so much. And so, even though it's complex, there's a lot we can do to make it happen.
I've got to say, I love the rocket backpack. I think the complex EDL system is fantastic. But to me, and maybe it's just the age that I came of, but, the concept that we would land the rovers before with the giant, the airbags, to me seems even more audacious. But, we're going to take this rover that we've spent all of this time and money on, and then we're just going to bounce it along the surface. I mean, that's, the testing and the creativity that the engineers bring to these sorts of things. And then the amount of testing that we go through to make sure, we really genuinely think this will work. I mean, that's what NASA really brings, right? That creativity and then the follow through to make sure that, this is the best way to do it. And so you can see it in all of the different aspects of MSR as well.
I love that so much. Yeah. And for a moment, I do want to talk, a little bit about you as a person before we go into our audience Q&A and some other parts of our show here. You told me before the show that you enjoy cooking. And I also love being in the kitchen. I think cooking itself is a fun mix of science and art. And I wonder, what things have you made in the kitchen? Have you really enjoyed kind of getting yourself into and making food?
Yeah. I used to work with a lot of chemists when I was a student. I did a lot of chemistry work, and I know a lot of chemists don't like to be in the kitchen because they're like, I do chemistry all day. I don't want to have to come home and do chemistry. But the exciting thing about cooking is it's chemistry you get to eat, which is always nice. But last year, my husband's birthday and Father's Day were on the same day. And so I thought I had to do something, really go all out. And I made a baked Alaska from scratch because that's his favorite dish. And that was such a fantastic combination of, temperature change and phase change and, using all of these different things. It's this process, made 3 different ice creams from scratch, and there was berries and there was, all of this kind of thing, and then making the meringue and then lighting the whole thing on fire. That kind of thing. It was just so much fun. I had a great time doing it. It was just a really fantastic opportunity. I'm always, different types of roast meats and things like that. I really enjoy chemistry and the kind of cooking that you do that involves, sort of longer periods of time, because you give these ingredients time to have these reactions, and the result is always delicious.
Yeah, I love it so much. I also do home brewing, and right now I'm trying out my hand at brewing kombucha for the first time. And I gotta say, I love working with organisms that also ferment our foods and beverages. It's so much fun to be connected to them. The biology, the science, exactly. It's a partnership in us making this delicious stuff that we consume. Now, I do have to mention this because I saw it online. You were not too long ago a contestant on the game show The Price is Right, and you won. What was that like?
So it was totally wild. We have some very dear friends who got tickets to the game show. We went and, did the whole process. And when they called, I genuinely was surprised to get called to come on down. But the whole process was, it's meant to be exciting, and it's meant to sort of, encourage and sort of bring out the most excited nature in all of us. I had a blast. I got to meet Drew Carey. I got to spin the giant wheel, which, to answer the question that everybody always asks, it was exactly as heavy as a giant wheel you would imagine would be. But the most exciting thing about it was just sort of feeding off the audience's energy. You may not be surprised that I enjoy that kind of thing, and that I've done a lot of theater in the past. So there was a point at it when I realized okay, this is real. You're on stage, but you're not acting as a piece. You're actually here. And I, won a whole bunch of fantastic prizes. But quite honestly, the most exciting thing was I won a trip to Boston, which I used to travel to Boston, drive up to New Hampshire, and officiate the wedding of two friends of mine, who I'd introduced a number of years before. So there was a very sweet connection in all of that. And it was just, the whole thing was exciting, but knowing that, there's sort of this continuation of that was really fun.
No, that's so beautiful. Let's treat our show a bit like a game show now, just for a moment. We have our Faster Than Light segment. These are just little short answers you can give us to a few of the common questions that people ask about those of us who've pursued careers in astrobiology. The first one comes from Enrico Fermi. What is your favorite answer to Fermi's question, where are they?
I think I'm going to have to answer like three pieces of answers, right? I think the answer is it's some combination of the universe is very, very big, right? And we think about, our planet, our solar system as being big, but, we're a tiny, tiny piece of a much bigger solar system. So there's a lot of room, right? So where are they? Somewhere out there. That's one piece. I think, most life is probably microbial, not that easy to spot. I think that there's good evidence, or there's good reason to think that microbial life is probably more common than more complex life. And then the third piece in this puzzle, I think, is we haven't been looking all that long. We, in terms of, human lifetimes, we feel like, well, we've been going to space, for more than half a century now. And, we've looked at all of these things and we've seen all these things, but really in terms of, time scales, the universe is very old, right? So the universe is very big and the universe is very old. I think that we just, just a little patience, I think, is the answer.
Groovy. You mentioned at the very top of the hour when we first started the show that you were inspired as a young person by reading, that you love books. So what stories have inspired you to want to pursue a career in astrobiology?
When I was a kid in Jupiter, we had a great used bookstore nearby. And it was like, honestly, it was right next to the movie theater. And so anytime I was over to the movie theater, I would always stop in the used bookstore and buy at least one new book, sometimes a couple new books. But, mostly Isaac Asimov, also Ray Bradbury or Arthur C. Clarke. I consumed a lot of science fiction as a young, impressionable, as a youth. And I think, it's hard to point to sort of any one story, but just the whole sort of framework of science fiction as a vision to the future, as a way to think about what might be out there, how we might go, what all of those kinds of things, how all of that fits together. I would sort of say all of that was really my inspiration.
Awesome. Well, let's talk about inspiration and young Lindsay in the early parts of her career. If you could go back right now to the beginning of your career and give yourself some advice, what would you say?
Ooh, that's a dangerous prospect. You're going to ask about time travel right after the science fiction question. No, anyways, I think I would probably, my dad used to have this quote, and it was, if you don't do it when you get to it, you may never get to it to do it again. And one of the things I said earlier, I have been lucky enough to have a lot of different experiences and, have a lot of opportunities that I was able to take advantage of. And all of them, even the ones that were not successful, right? Even the ones where, I didn't quite get out of it what I thought I was going to get out of it, really shaped who I am, right? There was always something I was able to learn or some new skill or something, so I would say, just keep taking advantage of those opportunities. I wouldn't want to change any of the things that I've done. I wouldn't say, don't do this or definitely do that instead or anything like that. But just, do the opportunities that you're lucky enough to take advantage of.
Absolutely. Now, given your roles at NASA, this next one will be interesting. If there is alien life out there, do you think we're more likely to find it from a world in our own solar system or on an exoplanet first?
Oh, I don't know if I can answer that one. It feels like trying to pick a favorite child, right? Do you think it'll be more likely in the solar system or outside of the solar system? I think that either way, there would be some really interesting conclusions that we may be able to draw from those things. I think finding life essentially right next door would really say something about the prospect for the amount of habitable environments there are within the universe. I think finding life somewhere else would say, life originates multiple places all over the place, wherever there is. So I'm going to say both are equally likely.
I love it.
With the information we have today.
You love both children equally. Okay, fair. I appreciate that. Now, as I mentioned before, you have several roles at NASA. You have a remarkable career. For our audience, though, what do you think is the best part of your job?
This one is going to sound very specific and a little bit cheesy. I actually love being able to send the funds out to researchers who have awards with us, right? I love reading their proposals or their annual reports and seeing either what they're hoping to be able to do or what they've already accomplished. It's sort of being able to, to peek over the shoulder on the very vanguard of the science. And I think that is super exciting. And then one of the benefits of being, part of the government is I essentially get to buy science on behalf of NASA. And I just, I think I love that part of it. It's kind of small and focused, but, this is the edge and this is the future and all of that. So that's one of my favorite things.
Oh, that's so awesome. Yeah. Helping out the next generation, helping out those amongst us who are our peers in the community that make great science and do great things. Pretty incredible. Our final question in our Faster Than Light segment is my favorite. What is one science fact that still blows your mind?
This one, I feel like there are a lot of science facts that blow my mind. So I'm going to go with the biggest one, right? And that is the reminder that we are all star stuff, right? That all elements come from stars. Some significant percentage of that, of the larger elements come from supernova, but that, every piece of who you are was processed in some star somewhere at some point. I just think that, that's a reminder that we're all part of something a lot bigger than than just us or the work that we're doing or, our friends and neighbors and, the connections. They just continue going outwards from there. And that, I think it's fantastic.
That's wonderful. Well, thank you so much for answering our questions for our Faster Than Light segment. We're now going to open it up to our live audience who are watching right now on YouTube and who have some questions. We're going to start off with a question that was asked a little bit earlier by Mohsen Salashore. Mohsen wants to know why we're using nitrogen gas for the samples from OREX, from OSIRIS-REx. And they wanted to know if maybe helium is a better choice. And maybe we can connect this to MSR as well. Why would we use nitrogen rather than helium as an inert gas for protecting our samples?
So one of the main reasons, of course, is that we use nitrogen, just to explain why we use nitrogen at all or any gas, is to sort of have an outward flow, prevent Earth contamination from coming in. And one of the reasons that we are most interested in using nitrogen, of course, is that there's a lot more helium in space. And so we want to make sure that if we're making some of those measurements, that's protected. So anytime that you make measurements, you want to make sure that the compounds you're using are not things that you want to measure along the way. When I was an organic geochemist working in the lab, we would try never, ever, ever to use plastics because plastics are very related to the kinds of compounds that we were looking to measure in these rocks. So if you use plastics on your samples, you're much more likely to find the plastics in the analyses that you do. And so that you want to use compounds that you're not ultimately later on going to want to go back and try and measure.
Awesome. We have another question that came in rather early from Dr. Jim Pass. Dr. Pass wants to know, in regard to sample return, what more can scientists on Earth do in terms of analyses that rovers and satellites simply can't?
So, the easiest and quickest answer to this is if you're familiar with a synchrotron, right? These are building-sized instruments And there are measurements that can be made with a synchrotron, non-destructively and other ways, and other things that you may want to measure where you're never going to be able to put a building-sized instrument onto a rover or into an orbiter. And so, it's those kinds of measurements, those kinds of things where, either you need something that's much, much larger than you could put onto a spacecraft, or something that requires sort of nanomanipulation, or something that requires, very small amounts measured in very precise ways, or, the sample needs to be held in a particular, all of those kinds of things can tell you a lot about the samples in ways that, you can only get, you either can't get at all, or you can only get, a much, much lower accuracy or precision with a spacecraft instrument.
That speaks to me a lot. I've done research on 3 different synchrotrons on our planet, and they are very large facilities. Now, we can build benchtop size particle accelerators in the future. People have been working on it for a long time, but even then, you're not getting the resolution you get at these large facilities. So that's pretty fantastic. We have a question from Zora Zahir on YouTube, who wants to know how debate about dating rocks impacts our interpretations of return samples, which is a pretty good question given how we do date the rocks currently on Mars.
Yeah. So, one of the most exciting things for the Mars 2020 team was when they made some of the first measurements, investigated some of the first samples from Jezero, and realized that we were going to have access to some volcanic rocks. And because what that means is that we can hopefully start making measurements that we can get, that higher resolution, that higher precision when we get those samples back, and be able to do a much better job of dating that impact event, and as a result, sort of calibrating what we call calibrating the crater counting curve, right? So the way that we date surfaces and understand how old surfaces are throughout the solar system is by looking at how many craters of different size there are within an area. And that is a relative dating, right? Things that have more craters are older, and things that have fewer craters are younger. Because that's a relative dating thing, we can kind of use it to understand a little bit about where the ages are of different units and such. But if we have an absolute date, this rock is this specific age, it can help us sort of calibrate that whole thing. Right now, we have a calibrated date from the moon, but the more calibrated surfaces we have throughout the solar system, the better we can make our estimates of other places in the solar system. So the more measurements we make, the better our estimates get, and then and it can sort of builds on from there.
Fantastic. We have a question that came in from Marina R., which is, what are the changes that Bennu samples tell us not only about our solar system, but other ones where it might be before? Interesting.
So the exciting thing about Bennu is that it is a carbonaceous asteroid that is pretty old, right? And so Bennu comes from a time that, sort of earlier than we saw, sort of planet formation and all that kind of stuff. And so the ability to understand, that sort of pristine material from much, much earlier in our solar system allows us to better understand, some of those early processes, some of the things that were going on when our solar system was starting to form early on and things like that. And to your question, until we started looking at exoplanets, I'll say, we were pretty sure that we understood, how the planets formed in our solar system, and that, of course, the way the planets formed in our solar system was a pretty good analogy of how planets must form elsewhere in other stellar systems. We found a lot of exoplanets that indicate there may be other ways that stellar systems may form and evolve. And so, the more that we can learn about exactly what happened in our solar system, the better we can sort of take those models and apply them to evidence that other things happen in other ways. So it's it's sort of each piece of information that you have sort of starts to build on the other pieces and allows you to have a better understanding, a better perspective of what we know and how we may be able to investigate the next things.
Absolutely. And just thinking about Marina's question, while Bennu certainly is from our solar system, it does make me wonder if in the distant future, perhaps we'll have some interstellar asteroidal or cometary material, and maybe we'll build a spacecraft that can go out and sample it, even though it's moving extremely fast. Sample return could one day be from samples from somewhere else, and that's kind of a cool idea as well. Exactly. Now, we have a question from Washington the Giant. It's an interesting question. We spoke before about planetary protection with our MSR samples. Washington just wants to know what the protocols are that we're going to be using for avoiding having things like melanized fungi to avoid having false positive biosignatures get into those samples when we bring them back. You kind of mentioned that structure before, but I think for Washington, they just want to know kind of how are we avoiding getting Earth material into the samples again?
That's a great question and a really important one, and one that we are, spending a lot of time and effort trying to make sure that doesn't become a problem. And so, like one of the things so as I said before, sort of in the samples in the container that we're planning to bring them back in, multiple levels of containment. That sort of multiple levels of containment would not be opened until we are in a facility that is particularly clean. How do we know it's particularly clean? Well, we have conversations with colleagues and folks across the government, with other agencies, other groups that do things like, run, BSL-4 facilities. These are the kind of facilities that we do, we test pathogens and things in. As you can imagine, in those facilities, it's very, very important that we understand, how material comes in and material goes out. So we use BSL-4 facilities as well as, what we call our curation facilities. NASA has a lot of experience making sure that we keep samples pristine from Earth contamination. The combination of those two things, right, keeping the material that's in from getting out, right, so that there's no concern about, backwards planetary protection, and keeping Earth material from getting in, which is still forwards contamination both of those things together are the things that we have to think about from our sample return. We have to think about in this facility, and that we're really working with, now designing all of those things so that by the time the samples come back, it'll be ready and we'll have these facilities in place.
That's fantastic. I will say, so we're getting close to the top of the hour. We have a few more questions I'd love to get to if we have time here. There's one interesting question from Daniel Lappin I see here on YouTube, wanting to know what's being done to develop, as they say, frontier methods to apply the most advanced thinking, creativity, and such to analyze samples to maximize science output, societal benefit, and economic impact of these missions. I will start off by saying, Daniel, if you're interested in seeing how NASA makes connections to everything that we do currently on the Earth, not just for our understanding of things like the climate and pollution, changes in the atmosphere, the ocean surface with Earth observing satellites, there's something called NASA Spinoff that you can look up. And NASA Spinoff for a very long time has been sharing information about the various ways that we actually get a lot of technology development and a technology transfer back from all of these NASA missions. But Lindsay, what do you think? What are the impacts that we can see from things like developing better sample return missions?
Well, so most directly, right? One of the things we're thinking about with Mars sample return is, the potential for sending humans to Mars. There's a lot of information that we can get from Mars sample return that would be particularly useful for sending humans there. Things about the soil conditions, right? Is there potentially anything hazardous in the soil condition or in the regolith there on Mars? Things about, could we use it as a protective material if we have humans on Mars? Beyond that, I think that there's a whole bunch of interesting aspects of this. As I was mentioning, there's a lot of, firsts in the Mars sample return campaign. And so thinking about, how we design spacecraft to rendezvous in space without people driving them and things like that. Thinking about, to go back to humans to Mars, thinking about launching off the surface of Mars, all of those sorts of things. A lot of times we do exciting things in NASA, not because we say, here's the spinoff that's going to make it worth it in the end, but rather, this is an exciting prospect. And, we do the new engineering feats and the new technical development, all that kind of stuff, not because of the spinoff, but because it's needed. And then it's up to other creative folks, perhaps like yourself, to think about, hey, there's a really cool piece there that I can tie to something else that I'm interested in. So it's a great point. And, NASA has, of course, had some really exciting spinoffs, as you said, Graham.
Absolutely. Yeah. And so we have two more questions here if we have time, both regarding asteroidal sample return. The first one from Shiva Agarwal wants to know how the samples from Hayabusa 2 are different from what OSIRIS-REx brought back. So how are the samples from Ryugu and Bennu potentially different?
Well, they are different asteroids. But the answer is, of course, like we said, being able to understand, slight differences in those samples and understand, we sort of think of asteroids as, monolithic. They're all out there in the asteroid belt, or there's some asteroids that are in other places. But how we can understand those differences is a great way. It starts to piece apart and take those assumptions. These are similar, so therefore they must be the same, and say, okay, but how are they different, and what can we understand better because we can understand those differences? And of course, the fantastic thing about Hayabusa 2 is that, we have, because we were able to get some of the material from Hayabusa 2, we are also going to be giving some of the material from OREX to JAXA for them to work on, and also sort of, speaking to the previous question, it promotes partnerships within science and science communities around the world.
Oh, lovely. Yeah, and that's the important part. We are working around the globe, scientists, engineers, artists, creators, thinkers, doers, dreamers, to make all of this happen, to learn more about our place in the universe. And it really does take a global community to make it all happen. We have one last question that I want to cover here. This is from Hendrik Holst on YouTube. Hendrik wants to know if there is any material in that Bennu sample that came back from outside of our solar system, would we be able to tell the difference? Now, I will say before I ask you to answer that, Lindsay, I'll mention to Hendrik to look up something called pre-solar grains. If you're interested in learning more, there are materials that formed some of the early meteorites and asteroids in the early solar system that did indeed come from other solar systems, other star systems from long ago, from far away. And the cool way that we know that is because of their isotopes. So we have a general isotopic composition in our solar system on our Earth that is fairly standardized across the entire solar system. It's the same as our sun has, of things like carbon-13, carbon-12. And that number is almost always exactly the same wherever you look. There are small environmental changes that can happen, but generally there's one specific number. We find these grains that have wild ranges of those isotopes, telling us that they came from other stars that had different starting compositions of those isotopes. But Lindsay, what do you think of materials? Let's not say just Bennu. Let's say materials from Bennu or Mars or any other sample return. How can we tell the differences between those materials that formed in place or came from somewhere else, like outside the solar system?
I think you hit the nail right on the head, Graham. There are compositional differences, isotopic differences that help us understand those things. I'll say that, those things are clearly not as common, right? And so it would certainly be particularly exciting to find something like that. I know that, there are multiple protocols in place when you have these sample return missions that are sort of the, oh my gosh, this is a really cool piece, sidebar. So, this is where the sample goes, and this is who gets to do this, and this is who gets to do that. But if you find an, oh my gosh, kind of piece, there's a, okay, then this is how we think about handling those pieces and the data that comes from that. I'll say the other thing I'll say is just, anytime that you go to explore, you find something that you weren't expecting if you're doing it right. And so, I certainly hope that we find some exciting things. I mean, we have seen evidence with some of our rovers of things that look like iron meteorites sitting on the surface of Mars or other things that are exciting like that. And so, the prospect of finding these things is not nothing, but they're certainly exciting when we find them. So, you answered it really well, but I'll just say, I hope we find something unexpected and exciting.
Absolutely. Expect the unexpected, and let's be excited together. Well, Lindsay, thank you so much for joining us for the show today. We do have to wrap it now. So for those who have questions still in the YouTube chat or watching the recorded version, please reach out to any of us to ask your questions about astrobiology. Reach out to Lindsay, reach out to myself, reach out to the NASA Astrobiology Program. We're always happy to try to answer your questions about this quest to understand life. Dr. Lindsay Hays, thank you so much.
Thanks so much for having me.
For those who are tuning in right now, if you want to learn more about the Mars Sample Return Program, we're sharing a link right now in the video that can share more information for how to find out NASA's approach to Mars sample return. Also, if you want to stay in the loop for upcoming episodes of Ask An Astrobiologist, as well as other events and activities, programs, opportunities through the NASA Astrobiology Program, please do sign up for the email newsletter. It's a great way to know what NASA Astrobiology is up to. There's so much great information and articles shared there. And so for all of you tuning in live, for all of you watching the recording later on, thank you so much for joining us. It's always a pleasure to have you come here ask your questions about astrobiology. So thank you for joining, and until next time, stay curious.